Now that we've gotten from our previous lesson a better sense of polynomials and how we factor them, we're going to now turn our attention to a study of the relationship between the sums and products of the roots of polynomials. So we're going to sort of look at when you have a polynomial and you know its roots, can you figure out what the sum of those roots and the product of the roots are, sort of just based on the coefficients. Today we're going to focus just on quadratics and looking at the relationships between their roots, and then in our next lesson we're going to look at general polynomial roots, so 4th degree, 5th degree, even 10th degree polynomials. Before we begin, let's go ahead and take a deep breath, and let's begin. So I mentioned that today we're really just going to be looking at the roots of quadratics. Okay, so suppose that you have a general quadratic, ax squared plus bx plus c, and I'm going to tell you that the roots are p and q. Okay, so the key point for today, the whole of the lesson comes down to these two formulas, right? The idea is that when you add together the roots of this polynomial, it will always be negative b over a. And when you multiply the roots of this polynomial, it will always be c over a. In other words, we can tell what the sum and product of the roots are going to be just by looking at the coefficients of this quadratic. Now remember that in this course, we have sort of a focus on analysis and the approaches that we use to mathematics. And one of the big ways that we approach mathematics is through proof. And so I want to talk about how could we prove that these relationships are true. Let's go ahead and start this proof the way that we start all of our proofs, with a consider or a let statement. So we'll say something like, consider the quadratic ax squared plus bx plus c with roots p and q. And then remember, when we know about the roots of a quadratic, it also means that we know about the factors. So now we could write a statement like, then it must have factors x minus p and x minus q. But now that we know that it has factors x minus p and x minus q, we might say, well, wait a minute, then shouldn't the polynomial be x minus p times x minus q? In other words, if I were to multiply this out, x squared minus qx minus px plus pq. I just got that by sort of distributing this all out. And then I could even, I could look at these middle two terms here, and I could sort of factor the negative and the x out of it. X squared minus p plus qx plus pq. And then I sort of look at this and compare it to the quadratic that I had and realize, I really wanted that leading coefficient to be a. And really, from the beginning of this problem, I could have had a constant multiplied on the outside of this, and it wouldn't have changed anything at all. When I put that constant here, I can see that my polynomial is ax squared minus a p plus qx plus a p q. And then at this point, we're actually almost done with this thing. There's a really neat thing that we can do. If this is what this is, then the coefficients have to match. So that means that specifically, I should be able to match up the linear part with this part. I should be able to say, yeah, that means that b's got to equal negative a times p plus q. And similarly, I should be able to line up the constant parts. That means that c has to be equal to apq. And now we're just one step away. If I just divide both sides of this one by negative a, we'll get p plus q, the sum of the roots, has to be negative b over a. And if I divide the other one also by a, I'll get that the product of the roots, p times q, has to be c over a. And these were exactly the the relationships that we mentioned at the beginning that we were trying to prove. So I wanted to go through this proof process because we're going to do a really, really similar thing tomorrow when we extend this up to general polynomials of higher degrees. So I hope that this proof process made sense. If you've got questions about it, please ask them here so that I can try and address them before we move into our next lesson. But now that we've got this skill, let's see how we can use it to solve problems. So a really simple application of this principle is the ability for us to quickly find a polynomial or some of its coefficients given the roots that we have. So suppose that you have this equation, and this equation has, this shouldn't say roots, this should say solutions. All right, so suppose that this has solutions 3/4 and -2, and you're asked to find the values of b and c. Right? We could remember that the sum of the roots sum of the roots, the sum needs to be negative b over a. So in our case, negative b over 4. And the sum of our roots in this case is, it's literally 3/4 plus negative 2. So continuing to work with that, that means 3/4 plus a negative 8/4, which is negative 5/4. So now we can say that the sum of the roots, negative b over 4, has to equal the actual sum of the roots, negative 5 over 4, and we can really clearly see that b here is 5. Yay. What about the product of the roots? The product of the roots, according to our principle that we learned on the just before, should be c over a, which in our case here is c over 4. But we know that the product of our roots is literally 3/4 times negative 2, which means negative 6/4. And now, just like we did before, that means that the product of my roots, c over 4, has to equal the product of my roots, negative 6 over 4. And from there, we can conclude that c has to be negative 6. And there we go. We found the values of b and c using this principle. Now, I do want to point out there is another way that we could have done this problem. We could also have done this by just taking these roots up here, turning them into factors. Taking these solutions, turning them into factors, and then multiplying those factors together and finding b and c. And that works fine for quadratics, but if you're working with a quartic, a fourth degree polynomial, multiplying out 4 factors can be really time consuming. And so this process can really be helpful. So when we extend it, we're going to want to remember and know how to do it here. So it's almost like we're starting with a simple example, and then we're going to build that up to something more complicated. With that said, there are complicated problems that we can still do with quadratics that we may also be able to do with higher order ones. So again, we're starting small and building up. So sometimes what you're given is you're given a quadratic equation, and you're given some roots or solutions to that thing, and they want you to find a new quadratic that has different roots. And so this one can be a little weird. I'm going to go through this one with you, and then I've got a couple more examples that you can try on your own. Right? So we're told that this thing has these roots, or these solutions. Okay? And so using what we learned before, this means that the sum of my roots, p plus q, what does the sum of my roots, what's that supposed to be equal to? Well, the sum of my roots is supposed to be equal to negative b over a. Oh, and so in our specific case, this means negative 2 over 3, which means 2/3. So we're basically given in this problem, we know that p plus q is 2/3. Okay? Now we also know something about the product of our roots. The product of our roots here has to be c over a. So in our case, that's 4/3. Great, so I'm going to add that to my list of things that I know. I know that p times q is 4/3. Now let's look at what I need to do. I need to find a quadratic. So it's like I've set up the things I know before. So now I need to find a new quadratic, ax squared plus bx plus c, that has these different roots. And so I want to point out, and this is really important, this a, b, and c here are not going to be the same ones, because otherwise the roots would have been p and q, not p plus q and, p plus 2 and q plus 2. And moreover, I need this quadratic ax squared plus bx plus c with roots p plus q, p plus 2, and q plus 2. It's shockingly hard to say. I'm not sure why. There's one more thing that we can actually do here that's going to make the rest of this problem easier. I actually don't need to have an a in front of this thing. And the reason is, suppose that I found this thing, and I found this quadratic, and my a value is 3. Couldn't I just divide this whole thing by 3, and it wouldn't change the roots at all? So it's almost like what we're doing from the beginning. If you really want to let the a stay there, is you can start this problem by saying, let a equal 1. And letting a equal 1 is just going to sort of force this computation to be a little bit easier on us. So now that we've got that out of the way, let's move forward, right? Let's go ahead and consider the sum of the new roots, right? The sum of my new roots would be p plus 2 plus q plus 2, the sum of those things has to be equal to negative b over a, but since we let a be 1, I don't even have a fraction here, right? This is nice, right? P plus q plus 4 has to be negative b. Now, you might be worried here because there's like 3 unknowns. Does that mean I need 3 equations? Maybe, but maybe better than that. Do you notice right here this says p plus q? Don't I know what p plus q is? Like, look up above. We knew that the sum of the original roots was 2/3. So I can just say 2/3 plus 4 has to equal negative b. And what that means is it means if I got a common denominator, doesn't that mean that 14/3 would be negative b? So b has to be negative 14/3. And there it is. I found one of the coefficients that I needed. Awesome. Right? Now, let's look at this for the product of the roots, right? So first we went through and we looked at the sum of the roots, the sum of the new roots. Now let's look at the product of the new roots. Okay? So as we continue and look at this, the product of my new roots is going to be p plus 2 times q plus 2. And I know that that's supposed to be equal to c over a, but my a was 1, so yay, that's easy, right? So foiling out the left side, pq plus 2p plus 2q plus 4 has to equal c. Now, here's the kind of magical part, right? I have pq plus 2 times p plus q plus 4 equals c. Now, just like we did before, don't I know what p times q is? Don't I know what p plus q is? Those are these values that were right up here when we figured them out for the original thing. The product of my original roots was 4/3. The sum of my original roots was 2/3. And now I just need to solve, write out the rest of this equation. This is going to be 4/3 plus 4/3. That's 8/3 plus 4 has to be c. So that means that 20/3 is c. Well, great. I have my b value. I have my c value. So the quadratic we need is a, so 1x squared minus 14/3 x plus 20/3. And there it is. We solved the problem. Remember I mentioned before that if I really wanted to, I could divide or multiply this through by something. If you don't like the fractions, you're great. Multiply through by 3. It would be 3x squared minus 14x plus 20. Both of these polynomials have those roots, have the p plus 2 and the q plus 2 roots. Now, this example took us like 6 minutes. I think that the next 2 that I have aren't going to take quite as long because we've seen the process. We know that we're looking for these p plus q and p times q things to show up somewhere. So if you feel comfortable after that last one, go ahead and try this one. We have a quadratic, not equation, a quadratic, 3x squared minus x plus 8 that has roots p and q. We now want to find a quadratic equation with integer coefficients that has these roots. So again, not an equation, just find a quadratic. So find a quadratic that has these roots. So let's see here. If I look at my original sum, p plus q, should be equal to positive 1/3. And my original product should be p times q, and it should be equal to 8/3. So I have these relationships for p and q. So it's sort of like, yay, this is my given information. Now let's look into our new polynomial. We need a quadratic. We need a quadratic x squared plus bx plus c. Just like before, I'm going to ignore this leading coefficient because I'm just going to let a be 1. So I need a quadratic x squared plus bx plus c with roots p squared and q squared. So let's look at this like we did before. Let's look at the new sum. My new sum will be p squared plus q squared. And I know that that new sum is going to need to be negative b. Okay? Now, I'm supposed to be looking for these original things to show up, and those things aren't like jumping out at me. So maybe we wait on that one for a moment. let's step sideways and take a look at our new product. Okay, our new product is supposed to be p squared q squared, which is supposed to be equal to c over 1, so I'm just going to write c. Now wait a minute here. I'm seeing that this is pq squared, and we can see up above that pq is 8/3. So 8/3 squared is 64/9, which is c. So great, we found one of our coefficients. Now back to this other one. I'm really not seeing this thing show up. It's almost like the closest thing we can think of would be to take this thing and square it. If I did p plus q squared, it would be 1/3 squared, right? That would mean that p squared plus 2pq plus q squared would be 1/9. Oh, this is so close. It's like, it's too bad there's 2pq's in the way. Like, if only there was some way for me to get rid of that. If only there was some way to get rid of that pq. Hey, wait a minute. pq is 8/3, right? So I can take 8/3 and I can put it right there, and that'll let me solve for that p squared plus q squared. So let's take that 8/3 times 2, and we still have the p squared and the q squared around it. So p squared plus q squared plus 16/3. Wait, I'm going to want that to be 9ths, so let's take a step ahead of ourselves. If I multiply the top and bottom by 3, this will be 9ths equals 1/9. So p squared plus q squared is negative 47/9, but we knew that that was supposed to be negative b. So we just found that b is 47/9. And that means that the polynomial they wanted me to find is x squared plus 47/9 plus 64/9, x plus 64/9. So as you can see here, sometimes you have to be a little bit sneaky to figure out how to get these new relationships. But anytime it's asked, there's a way to find it. There's a way to work through it. So I've got one more example now. So this time you've got the quadratic 3x squared minus 2x plus 5, and it has these roots. Find a quadratic that has these roots. Sorry for all the mistakes I'm using with my vocabulary here. Clearly, I need to practice it too. So pause the video, try this one on your own. Remember, find the relationships for the old roots, and then try and find ways to use those to figure out relationships for the new roots. So my previous sum was p plus q had to equal negative b over a, and my previous product of roots, p times q, had to equal 5 over 3. So this is the information that I have to work with. Now I want to find x squared plus new bx plus new c with roots 1 over p and 1 over q. So I'm actually thinking that the product, we noticed last time, for the hard ones, the product seems to be easier to figure out first. So my new product would be 1 over p times 1 over q, and that's supposed to equal c. So 1 over pq has to equal c, but pq was 5/3, so 1 over 5/3 has to be c. That means c is 3/5. Oh, we're already halfway there. Now let's look at our new sum. Our new sum would be 1 over p plus 1 over q, and that has to be negative b over a, but my a value is 1. Now, we see this. Can you think of any way that we could manipulate that or rewrite it, sort of like move things around in hopes that we can get these expressions to show up? Hopefully an idea that popped into your head was, well, we could try and get a common denominator, like see what happens. So if I multiply this one by q over q, and I multiply this one by p over p, oh, cool. What I wind up with is q plus p on the top, and my common denominator is pq on the bottom. Wow, that's like literally the information that we were given up above, right? The numerator here is 2/3, that's the sum. The denominator here is 5/3, that's the product. So if I simplify these, that means that 2/5 has to be negative b. That means b has to be negative 2/5. Now that I have those two pieces of information, I can put them together to write the quadratic that they wanted. X squared minus 2/5 x plus 3/5. So that's the end of this lesson. These are the types of things that we can do using these relationships about the sum and product of the roots of quadratics. Now remember that our goal here is to sort of deeply understand this stuff so that we can apply it to higher order polynomials in our next lesson.